So yeah, this is Proofs Review 1 presentation. So I got the problems number 1, 4, and 7, and my name is Graham Lowe. So problem 1, this is going to be a direct proof. The result that we'll start with is let A and B be elements of uh, Z, so they're integers, and then if 3 divide 2a plus b, then 3 divide 7a plus 31b. So using direct proof, we'll assume that 3 divide 2a plus b, and I'll use my mouse here to just follow along. Um, and then we will break this into an equivalence. So 2a plus b equals 3y, where y is some integer. And that's just, the different way of writing it to say that 2a plus b is divisible by 3, or 3 times multiplied by some integer y is equal to 2a plus b. So we're gonna step through the next portion, but before we go into that, we want to basically show if 7a plus 31b is divisible by 3. So we're going to use this equivalence, and especially use 3y to kind of break down 7a plus 31b into a form where it's something times 3. And then we can uh, find the proof there. So if that made a little bit of sense, let's keep going down to the next piece. And sorry, I don't know who I'm presenting to audience wise. It's kind of funky that way, but yeah, so we'll just keep going. Um I'm assuming I'm presenting to a student, but yeah, so we'll keep going here. So thus 7a plus 31b. And like I said, we want to break this down, so we're trying to look for the form 2a plus 5b somewhere in here. So we'll start by breaking down 7a into 2a and 5a. And then we'll break down 31b into 26b and 5b. And then we have this nestled in here, this 2a and 5b. So we can substitute those out for 3y. And then we're left with the 5a and 26b over here. So we've gotten this equivalent, but it's still not super clear to me how this is divisible by 3. So the proof then goes on to break it down one more time. So we'll take this 5a and we will break it into 2a and 3a. And then we'll take this 26b and we'll break that one down into 21b and 5b. Then we will substitute in again. So we have this 2a and we have this 5b. And back up at the top here, we know that that's equal to 3y. So we'll substitute that in. And we get 3y plus 3y plus the remaining 3a here and the remaining 21b here. So now this is looking quite nice because every term here is divisible by 3. So the next couple of steps will be quite revealing. So we will factor out a 3, get the form 3 multiplied by y plus a plus 7b. And then the cool part here is that since we assume that y is an integer, and at the very beginning we assume we let a and b both be integers, we, due to the assuming properties of integers, we can know that all of these added together is also an integer. So we know that the thing that we broke down originally, this 7a plus 31b, we're just breaking it down, itself is divisible by 3. So yeah, just to restate that as a summary sentence, since everything inside the parentheses, y plus a plus 7b is an integer, then we know that 3 divides 7a plus 31b. So it's quite nice. It's like just a direct proof with substituting in a term. So it's a short one, but pretty cool. All right. So the next one is problem 4 that I got. So the result is there is no real number x such that x plus 1 over x equals 1. This uses a proof by contradiction. So the important part here is we're going to assume to the contrary, and then we're going to look for, as we start to solve, is there any contradiction with the contrary um, statement? So another way to say that is basically we think that what's written up here in the result is like true. So we're going to take the contrary of the result and see if that's false. And if we can find that the contrary is false, then we'll know that this original result is true. So let's like dig in and look at the example. So we're going to assume to the contrary that there existed a real number x, because up here we said no real number x, such that x plus 1 over x equals 1. So yeah, just the opposite of our original result. Then we go on to say x plus 1 over x equals 1. And we're just going to like simplify algebraically to make this give some better understanding here. We just note that x can't equal 0 because that would not work with 1 over x here, give us undefined. So we are going to take this and try to get rid of this like 1 over x because it can be easier to work with polynomials and get solutions to polynomials, like quadratic polynomials. So we're going to multiply both sides here by x, as you can see in this second step. So x multiplied on the first side, and then that 1 is just also multiplied by x, which is congruent to x squared plus 1, because that simplifies out. And then on the other side, we have 1 times x equal to x. So this all is, we're going to make that equal to 0. So we're going to bring the x over here, subtract it from both sides. Then we get the form x squared minus x plus 1 equals 0. Now, it's not exactly super clear to me like how to find our zeros for this polynomial. So the proof does go on to use like the like negative b plus or minus b squared minus 4ac all over 2a to get the solutions for this. So just breaking that down, like in front of x, we have a, and then, in front of the middle term, there's b, and then in front of the second term, there's c. So a in this case is 1, b in this case is negative 1, since we have minus x, and c is 1. So using that formula to look for solutions, we plug all that in, like the a and b and c, in the formula I mentioned earlier, and then when you start to simplify it, so this, negative 1 with another negative becomes 1, and then plus or minus the square root of this negative 1 squared becomes 1, and then, this 4 times 1 times 1 becomes a 4. And then on the bottom here, the 2 times 1 is just a 1. So this itself, we can simplify underneath the square root and then get negative 3. So this is the important part, where it's kind of revealing to the proof, because we have a negative number underneath the square root, which is going to give an imaginary number, which is outside of the scope of real numbers. So keeping that in mind, like we've come to find the solution for this quadratic formula to be imaginary, complex number here. So since this 1 plus or minus square root of -3/2 is imaginary, it contradicts the fact that, sorry, just moving my little recording window there. It contradicts the fact that x was assumed to be a real number. So this is where the proof by contradiction has the power, because it contradicts this initial assumption to the contrary, that x was a real number, proving that our contrary statement is false. This it's given a imaginary solution, so x is kind of a real number and not a real number, so it's like contradicts itself inside of here, which then goes on to prove that the original result using proof by contradiction is true. So in summary, there's no real number x such that x plus 1/x equals 1. Excuse me. So yeah, that's a pretty nice proof by contradiction there. We'll move on to the next problem. Number 7. So this first part, this proof is a little bit longer, but the first part is quite dense for me, so I stepped through it a little bit slower. So the result up here in black starts with, for each positive integer n, let a1, a2, ... an be n integers such that ai is congruent to mod 3 for each integer with 1 less than or equal to I, less than or equal to n. So this is a little bit complex, but what this is saying is that there is a series of that we're referring to as like a1, a2, and then going on to an. And for each of the elements in this series, they're of the form 2 mod 3, which is basically another way of saying that each element is divisible by 3 and then has a remainder of 2. So that's like a easier way for me to state this first sentence of the result. So yeah, like keep this piece in mind as we continue. Each element is divisible by 3 and gives a remainder of 2. So then we go on to look at the thing that we're trying to prove, and this proof is going to be a proof by induction, as we'll see later on. So it says then a, and these are all multiplied by each other, so a multiplied by a1 multiplied by a2 all the way to an is congruent to 1 mod 3 if n is even, and a1 multiplied by a2 all the way to an is 2 mod 3 if n is odd. So this will be better explained as we step through, but it's basically saying that if you have an even number of terms, which is another way of saying, if you're looking at the eventh term, like the second term, the fourth term, any even terms, then everything before that term multiplied by each other, if even, is divisible by 3 and gives a remainder of 1. Then for the odd case, this result is like posing, and we're going to prove that if you're on any random odd term, it could be, the third term, it could be the 17th term, then you multiply all the previous terms in the series by each other, then you will get something divisible by 3 with a remainder of 2. So again, quite a lot's going on up here, but proof by induction, it starts off simply and then we work our way up. So it's a nice way to approach this one, especially when we have series. So let's start with the base case and we'll get some more understanding. So the base case, we just have we're gonna split this up because we're looking at like even and odd and trying to prove two things here. So we're gonna look at the odd case first, odd base case. So if A is 1, oh sorry, I had so if if the first term of the series, um, oh sorry, not if. Let me restate. So the first term of the series, due to the first sentence, uh, is congruent to 2 mod 3, which again is just saying that the we've stated originally that each of these terms is going to be congruent to 2 mod 3. So if we take the first term, which is also an odd term, then it is congruent to 2 mod 3. But is this true for the second sentence over here? So it is odd because we're only looking at one term, the first term. So that itself multiplied by, nothing else because it's just the first term is equivalent to 2 mod 3. So this statement here is true for the base case for odd. Then we go to the second term. So what if I equals 2? We've looked at A1, what about A2? So for A2, it is also congruent to 2 mod 3 because as we said in the first sentence up here, each term in this series, each element of this series is going to be congruent to 2 mod 3. But then we want to look at our second sentence down here and see if it's also true. So we're going to look at the even case and see. So we know from our first base case that A1 is congruent to 2 mod 3, which can be written in that other form, kind of like I alluded to earlier, that it's divisible by 3 and gives a remainder of 2, or congruently 3x plus 2. So some integer x times 3 plus 2 gives a 1. And we've we have also have this a2 over here, where a2 is of the same form, but we're going to use a different variable y here, which is also an integer. And using the same logic, a2 equals 3y plus 32, just because each element, and I might be over-explaining this, but just restating because we have kind of like two different series, like one listed out here and then one where they're multiplied by each other. But yeah, so for each element, A1 and A2, they're of this form. Now we want to see for the even case, since we have A2, if these two terms multiplied by each other, so A1 times A2 is congruent to 1 mod 3. So we'll take A1 and A2, multiply them by each other. That gives us 6xy plus 6x plus 6y plus 4. Then we will move around. We will break down this 4 into a 3 and a 1 so that we can then take a 3 out of each of these terms. We get 3 multiplied by 2xy plus 2y plus, or sorry, 3 multiplied by 2xy plus 2x plus 2y plus 1. And then all of that plus 1, which is another way, when we go back to the different ways to write mod, to basically say 3 times something plus 1 is equal to this over here. And another way to say this is 1 mod 3, just with the way that modulus works. So our base case is checks out when n is even. So in this case, n was even, and we did get what our result had stated, that for even, we'll get 1 mod 3. So yeah, that was a lot, but hopefully that is uh, that's able to be seen based off what I said. Now, since we're doing induction, we have our base case, then we're going to take some integer k. This is the like power of induction. So we're gonna take it inductive hypothesis. Assume that what is stated up here holds for some integer k. Now we have even and odd cases, so again, that's why this question number 7 is complex, because we're doing induction, we're doing two cases. But let's start with the case 1. Assume k, some integer, is even. So we will have this form where we have a 1 multiplied by a2 all the way up to ak, and then we will have a k plus 1 multiplied if we were to just extend that out to one more element. And we want to see what happens when we start to substitute in and see if things kind of contradict themselves in this induction. So what does this form actually say? A1 multiplied all the way up to AK. Well, this is when k is even. So another way to say this is like our second base case, or like the first part of this second sentence. Since it's even, it is congruent to 1 mod 3. Or another way to write that, like we wrote over here, it's congruent to 3 multiplied by some integer p, which we're just p and q we're assuming as integers here, plus 1. So that might be a little bit confusing, but we're basically substituting in a multiplied by a1 multiplied by a2 all the way multiplied to ak, because our result says that is even, and also that is, or we're assuming that is even, and our result says that that's congruent to 1 mod 3. So we're going to substitute that in. Sorry, I might be over explaining again. But then, now what does this ak plus 1 going to be congruent to, equivalent to, you know? So since k is even, k plus 1 will be odd. And, oh no, sorry, that's not true, but k plus 1 itself is a element of this series. So by the first sentence, k plus 1 for both of these cases is actually going to be equal to 2 mod 3, because we're saying that each of these is itself is equal to 3q plus 2, or 2 mod 3, where q is some integer in is some integer. So this form gets is congruent to this form here, 3p plus 1 multiplied by 3q plus 2. And then we're just going to solve this out, and we'll reveal something towards the end here. So that gives us, 9pq plus 6p plus 3q plus 2. And then we're going to look for a 3 and this 9, 6, 3, and we'll pull that out. So we get 3 multiplied by 3pq plus 2p plus q, and then all of that itself plus 2 again. So what does this look like? This itself looks like the form 2 mod 3, or 3 multiplied by some integer, because these are all integers, plus 2. So we've basically proven in case 1 here that k is even. We're substituting in sorry, give me a second here. Okay, yes. So for case one, we want to so we've gotten this far, and induction, the power of induction is looking at k plus 1, like the relationship between k and k plus 1, and seeing if something is assumed for k can be true for k plus 1. That's the way these like proof by inductions are built. So now that now let's look through the lens of k plus 1, and knowing k plus 1 to be odd term in this case, uh, since k is even, k plus 1 will be the odd term, we can look at this form over here, which is equivalent to 3 integer plus 2, or 2 mod 3. And we can show for this case 1 that an odd k plus 1 is congruent to 2 mod 3. So you might be expecting, oh, this should be 3 multiplied by something plus 1 for k because k was odd. But what we've actually done is we're not looking at the k case here, we're looking at the k plus 1 case here. We're assuming some integer k, and then we're looking what happens when we examine k plus 1. So yeah, that's case 1. And then case 2 is assuming k is odd, which would then imply that k plus 1 is even. And we'll see, does k plus 1 hold if we assume that k is odd? So when we do our multiplication here, we have a similar form, but when we substitute this time, k plus 1 will still be 3q plus 2, because it's just another element of the series, and each element is 3 integer plus 2. But this multiplication here, since k is odd, is actually of the form 2 mod 3, because we said up here in the result, if n is odd, it's of the form 2 mod 3. So we're going to substitute in 3p plus 2 since k is odd. Then when we solve this out, we get 9pq plus 6p plus 6q plus 4. We're going to look for a 3 again, pull that out. So we get 3 multiplied by 3pq plus 2p plus 2q plus 1. And then all of that plus 1. Just moving my little recording window here. So again, what does this mean? So this means that when we look at k plus 1 being even, k is odd, k plus 1 is even, does it give us the form that k plus 1 is 1 mod 3? And it does, because 3 is being multiplied by some integer plus 1. So that's congruent to 1 mod 3. So we've solved both cases where k is even, k plus 1 is odd, and k is odd and k plus 1 is even. We've assumed some base cases here, so we can basically use induction to extend this out across integers, all integers in this case, positive integers. So the summary statement is, therefore, by PMI, we have shown the result to be true. And just like I said, it's basically extending out, assuming some base case, and then can we assume some k and then extend it out over k plus 1 for just like a some integer k, any random integer k. So hopefully that makes sense. It is complex due to the fact that there's multiple cases built into the induction, but that is the way that this proof approached it, and it did work out quite nice to just break it down by odd cases and even cases. And we had to flip back and forth between seeing if stuff was even, seeing if stuff was odd, but yeah, just step back through the beginning if some of the later parts were difficult. And I think even when I was talking about case one, I messed up myself here thinking about k is even, k is odd, but yeah, at the end, we did show the result to be true by proving both of these cases. So yeah, thank you, and I think this concludes my presentation.